In this lecture, you are going to learn about elongation due to axial loading. Elongation due to axial loading. Okay, so now suppose there is any bar which is mounted to some wall here. So this is the initial configuration of the bar when there is no subjection of any type of load. So suppose at this time the length of this bar is L. Now when we are going to subject some load on this bar, then its configuration changes and it looks something like this thing. So we can see that there is a change in the length, that is some increase in length. We can call it as delta L and delta L. Okay, so we have seen that sigma is equal to P by A, that is the axial loading equation, is equal to Young's modulus times the strain, which is equal to Young's modulus multiplied by change in length upon original length. So we can calculate the change in length by bringing L to this side, that is change in length is equal to P multiplied by L divided by A times E. So we can write P by A, that is this term, P by A term, as a sigma, that is the stress. So we can write sigma L by E. So this equation is valid. This particular equation is valid. This particular equation is valid when quantities are not varying with length. When the quantities in the equation, when the quantities in the equation are not varying with length, are not changing or varying with length. Now suppose if the quantities are varying with length, so we are going to use the equation delta L is equal to integration of from 0 to L P dot dx by AE or 0 to L, we can write sigma dot dx by AE, not AE, it will be E. It will be E. So this equation is valid. So this equation is valid when quantities are varying or changing with length. So here the quantities can be is the function of AX, that is when the area is varying. Suppose the arrangement looks something like this thing. When area is varying, so this is the variation of the area. Um, so this is the total variation of the area which we are talking about. So we are going to consider AX, and if the load is bearing, then we should consider P is equal to P of X, or if the Young's modulus is varying, we can consider E equal to E function of X. Now we can compare this schematic diagram with the spring system. So after comparing this diagram, this spring system, it will look something like this thing. And let me clear this thing up. So it will look something like this. So this is the spring system. It is subjected to some load P, and there is a change in configuration, that is delta. So here we can rewrite the delta L term. So delta L, we can write, so this term we can write it as, so here, so delta L is equal to P upon E A by L. So we can write this EA by L as K, so it is basically P by K, and here K is equal to longitudinal stiffness, which is EA upon EL. So this is the representation of the longitudinal stiffness and how to calculate it. So in the next lecture, we are going to deal with some numerical problems. So for now, thank you.